Hi dear students, welcome to this video. Today we discuss some individual members of carboxylic acids. We have hydroxy acids, carboxylic acids containing OH group as well. Members are lactic, malic, tartaric and citric acids. We will discuss the first three first, and these we have to discuss only the structure, and regarding citric acid we have a detailed discussion. The first in the first three carboxylic acids, lactic acid is a monocarboxylic acid, whereas malic and tartaric acids are dicarboxylic acids. Citric acid is a tricarboxylic acid. For these three we have only structure to discuss. First one, lactic acid. The IUPAC's name is 2-hydroxy propanoic acid. So it is 2-hydroxy propanoic acid. This is lactic acid. The source is, lactic comes from lactose. So it's obtained by fermentation of milk sugar, that is lactose. It is a chiral molecule. You might have discussed these molecules sometimes in stereochemistry earlier. This is a chiral center. So we can draw the Fischer structure, Fischer projection. COH is written at the top, the most oxidized group, OH, H and CH3. Okay, we know this is the D form compared to glyceraldehyde. You will have the enantiomer, the mirror image, that is the L form for this one. The next one is malic acid. It is otherwise hydroxysuccinic acid. We have learned about succinic acid, which is a dicarboxylic acid, CH2COH, CH2COOH. This is succinic acid. It's we can also call it butane 1,2-dicarboxylic acid. That's a strict IUPAC's name. And there is one OH here. For example, 2-hydroxysuccinic acid. So the difference compared to lactic acid is that this one, see, CH, OH, this is the same thing here, and here it is CH2COOH. That's all. Now this is malic acid. Malic acid is to be distinguished from malic acid. Malic and fumaric acid, which we discussed earlier. It's an unsaturated dicarboxylic acid. This is malic acid, and malic acid is rich in sour apple. Okay, and coming to, so this also will have the enantiomer, the D and L form. Okay, now coming to the last one, tartaric acid, and this is very familiar to you. You might have learned detailed about the stereochemistry of tartaric acid, right? Tartaric acid, 2,3-dihydroxysuccinic acid. That means here also there is an OH group. So it has two chiral carbons, right? So there are two COH and two OH. So I can draw the Fischer projection of tartaric acid. See how many stereoisomers are the optical isomers are there for tartaric acid? There are three. You might have learned this. Let us draw all of them. This is a recollection only. So COOH, here also COH, and you have two OH groups. Okay, I am writing H and OH here. See, this is tartaric acid, and OH on the right of this bottommost chiral carbon, you know, that's how we call it D, capital D, not dextro, small d, D form, and it is found to be levorotatory actually as far as the optical rotation is concerned. So this is D-tartaric acid, okay, and its mirror image will be what? The L form or the dextro form, I mean capital D, okay. So we can draw that structure, the mirror image, OH, H, like this, CO2H, CO2H. So this is the L form, right? And it is dextro. And one more form, what is that? If both OH are on the same side, you get another isomer, CO2H, CO2H. OH is on the same side. What is the speciality of this isomer? This is optically inactive. Why? Because of the presence of plane of symmetry, you know that. Internal compensation. So this is called mesoform, meso-tartaric acid. So that's about these three members. Now regarding tartaric acid, it is found to be rich in grapes, especially in grapes. Okay. Now let us go to the detailed chemistry of citric acid. See, citric acid is a tricarboxylic acid. Okay. First, let us note the structure of citric acid. Citric acid is otherwise called 2-hydroxy propane 1,2,3 tricarboxylic acid. So it is like this: CH2COOH, then COH, COOH, CH2COH. Look at this. See? It is 1,2,3 tricarboxylic. It is propane 1,2,3 tricarboxylic acid, and you have a 2-hydroxy. This is also called beta-hydroxy carboxylic acid. I mean tricarboxylic acid, that's another name. Tricarboxylic, that's a common name. What is tricarboxylic acid? That is, if this is not there, what do you get? CH2COH, CHCOH, CH2COH, that's called tricarboxylic acid. And if it is OH here, it is 2-hydroxy or beta-hydroxy. So this is another common name, trivial name for citric acid. You know, citric acid is rich in citrus fruits, isn't it? We know that. That's the name, citric acid. Rich in citrus fruits, lemon, etc. Now coming to the various aspects. First of all, preparation. We have two important preparations, out of which Reformatsky reaction is particularly mentioned in the syllabus. First of all, from glycerol, reactions are here. Listen well. Glycerol, okay, is converted into citric acid. What is this route? First step, treated with HCl. What happens? The two primary alcoholic OH is substituted by Cl. You know the reaction of alcohols, substitution reaction. So it is minus 2H2O. So this and this OH get replaced by Cl. In the next step, it is a mild oxidation using maybe dilute HNO3. So that the secondary alcohol become ketone. Because oxidation is, you know, removal of hydrogen, so H2 is lost and it become ketone. And now we are adding HCl. This is the reaction of carbonyl compounds, aldehyde and ketone, nucleophilic addition reaction. On adding HCl you get what? Cyanohydrin. So this is cyanohydrin. 1,3-dichloro propane cyanohydrin it is. So the idea is to make this acid group later. So added. Now both Cl is replaced by CN. We know the nitrile synthesis of carboxylic acid, remember? So again it is, now it is SN reaction that is nucleophilic substitution reaction of alkyl halides. Both the Cl replaced by Cn, 2 molecules of KCN. So there are now 3 CNs here. Finally, acid hydrolysis. What happens? All CN become acid, isn't it? You get citric acid now. So this is one method. The second method is a special one by Reformatsky reaction. What is Reformatsky reaction? Reaction of alpha bromo ester. See, this is an ester, right? Alpha bromo. Alpha bromo ester reacts with aldehyde or ketone like carbonyl compound in presence of zinc. Zinc is the key metal in Reformatsky reaction. Like magnesium in Grignard synthesis. It's similar. So, we are starting with this compound here. This compound is ethyl oxaloacetate. See, this part is coming from oxalic acid. This is basically this is ethyl acetate, isn't it? What is ET written? ET stands for, I have told you earlier, C2H5 group, that is ethyl group. So ethyl acetate. But this is another substitution which is simply called coming from oxalic acid. So the starting compound or this ketone is ethyl oxaloacetate. Okay, ethyl oxaloacetate. That is the starting compound. So this is the carbonyl part, zinc is there, and this is alpha bromo. This is ethyl acetate, alpha bromo ethyl acetate. So what's the reaction? The reaction is this, similar to I said Grignard reagent. This zinc will first get incorporated into this, forming a organozinc compound. So it becomes ZnBr. Okay, we know this zinc being electropositive, this become negative and this become positive, and now it attack. This is a nucleophilic attack on this carbonyl carbon. Very similar to Grignard reagent reaction. So what happens? Look at this. This become O. This ZnBr will attach here. So OZnBr plus minus, and this part, negative part, get attached to this carbon. Okay, you get this. And finally hydrolysis. On hydrolysis, all ester groups get hydrolyzed. Okay, you get hydrolysis like this. This is also hydrolyzed. All become acid now. This also get hydrolyzed. Okay. Or more appropriately, it should be shown like this, not like this. This is how. Okay. Right, here also it is H here and OH here. So you are getting here, see this, what about this one? This also will break like this, hydrolysis takes place, you get this one. Finally, you have ZNO, HBr and 3 molecules of ethanol and you get citric acid. Okay, that's Reformatsky reaction. Finally, from lemon juice you can isolate citric acid. How? How citric acid is obtained from lemon juice? Lemon juice contains roughly 6 to 10% of citric acid. Okay. First thing is you boil it. On boiling, protein present in lemon juice get coagulated and it can be filtered off. Okay. So protein is removed. Now you add lime, calcium oxide. What happens? That will form the salt with citric acid, because citric acid reacts with lime, which is base. So it gets calcium citrate. That is precipitated now. Again filtered. You filter off calcium citrate. So it will be now pure form. Impurities will be in the mother liquor. Now the calcium citrate precipitate is now heated with sulfuric acid or it is dissolved in sulfuric acid, what happens? It will form calcium sulfate, which is insoluble. That will be the residue, and citrate will go into the solution as citric acid. That means calcium citrate is dissolved in sulfuric acid. So you get a solution, a soluble form of citric acid. Calcium sulfate will be the residue which is filtered off. And now you concentrate it and cool it. On cooling, you will get crystals of citric acid. In addition to this, citric acid on large scale, it is manufactured by the process called fermentation. Fermentation of glucose, sucrose, etc. will give citric acid in large scale using various fungi and molds. Okay, now we go on to the reactions. Reactions of citric acid. In the reactions, we can divide the reactions into three types. Citric acid contains two functional groups. There is, so remember, it is a tricarboxylic acid. Okay. It has acid group. So reaction due to acid group COH that include acidity, that means reaction with base, and also esterification, that means reaction with alcohol. Then reactions due to OH, there is one OH, right? That can give reaction that is acetylation, replacing hydrogen by acetyl group. And there's another reaction reduction. And finally, reaction involving both OH and COH, that is pyrolysis, action of heat. Okay, so let us consider the first one, reactions due to COOH group. So let us write citric acid. Reaction is very simple here. Since citric acid is a tricarboxylic acid, it's very clear that it can form three series of salts with bases. If you add one molecule of NaOH, one equivalent of NaOH if added, it will form monosodium salt. And it is that this acid is more reactive, maybe because of the presence of OH. So you get the first, I'm writing here itself, it becomes COONA, monosodium citrate. On adding another molecule of NaOH. Now these two are equivalent positions, right? Interestingly, citric acid is not optically active. Why? Because these two groups are similar, identical groups, so this carbon is not chiral. Okay. So next you can change this one. This is forming the salt, so disodium, and finally the third equivalent of NaOH will replace this H also, forming the trisodium salt. So that's a reaction with base. Coming to esterification. When you esterify citric acid, increasing number of alcohols can react. When you are adding one molecule of alcohol in presence of acid, for example, catalyzed by acid, any of this acid group will get esterified, is equal chance. So there are two possible isomers formed. So the monoester, these two are equivalent. So one will be replacing this, reacting with this COH, alcohol can form the ester, that is CH2COOR, COH, CH2COOH. And the next one is, if this is reacting, then the ester is CH2COH, COOR and CH2COOH. So there are two isomeric products, monoester. On further reaction, if you are adding another molecule of alcohol, you get the diester, dialkyl citrate. Again, there are two possibilities. Either these two get esterified, this already done, and this one, or these two. I mean this one and this one. So there are two possibilities. So that means one is ester group can be one here and the two end carbons like this. Okay, so 1,3 it can come at the 1,3 carbons, or it can be 1,2 like this. CH2 COOR COOR, OH is there, CH2 COOH. So these are the two diesters or dialkyl citrate. And finally, if you are 1 mole alcohol, you get only one product. All the acids are replaced. So there is no isomeric product possible here. It is simply you get only one product. That is the trialkyl ester. You understand? So that's about esterification, reactions due to acid group. Coming to reaction due to OH. There are two reactions to discuss. One is acetylation, and the other is reduction using HI. Look at the reactions. Citric acid, acetylation. You know, acetylation can be done using acetyl chloride or acetic anhydride. You know that? We learned in the acid derivatives in presence of bases like pyridine. So this OH group get acetylated, that means H is replaced by this one. So HCl, you know, this is what happens. This is the nucleophilic acid substitution actually. So you get the product, that is, you get acetylated acetyl citric acid, right? This become OCOCH3. So this is acetylated. OH is acetylated. CH2COOH. Acetyl citric acid. Okay. Now finally, only one product because only one OH. Next is reduction. Reduction means you are treating citric acid with HI. Reduction using HI. Okay, that's what. Not the reduction of carboxylic acid they are discussing here. So what happens, you know, this HI can break this OH group and H is added on this carbon and I here. Another HI also will come and form iodine and water. So the product is what you are getting, CH2COOH, CHCOOH. CH2COOH is the main product. What is the name of this product? I told you at the beginning. This is, IUP's name is propane 1,2,3 tricarboxylic acid, or common name, what is that? Tricarballylic acid. Plus, byproduct will be I2 and H2O. Okay. Now finally, reactions due to OH and COH. That is pyrolysis, means action of heat. It is an interesting reaction of citric acid when you heat it continuously for a long time. You get a series of products, okay, by dehydration as well as decarboxylation. Let us see that. Be careful. Let us write citric acid, CH2COOH. OH here, CH2COOH. Okay, this is heated. Maybe you can use sulfuric acid for dehydration. And what happens, you know, it is minus H2O. First of all, it undergo dehydration. That is, OH from this and one H from this will go. That is the first product. What do you get now? It is now CH, it become an unsaturated acid. CHCOOH, double bond here, and COOH, CH2COOH. This product is called aconitic acid. Names are very special. Aconitic acid, right? Now, if you are further heating it, still high temperature, that's by pyrolysis, long heating, what happens, it will lose carbon dioxide. That means now it is decarboxylation. And based on which COOH get decarboxylated, you have two products possible. Remember that this is intact. It is either this CO2 or this CO2 is going. Suppose this CO2 is going first. This carbon dioxide is lost. What do you get the product? The product is now CHCOOH, double bond, COOH, and this become what? CH3. Okay. This is what is known as citraconic acid. The next product, citraconic acid. See that this can exhibit cis trans isomerism because the different groups are connected here. This is actually cis isomer. It has a trans isomer if groups are on opposite side. That's called misaconic. That's called misaconic acid. Okay, this is the major one. And in addition to this, another product possible is, suppose it is this acid get decarboxylated. This is gone. Then what you get? This becomes CH2, double bond, COOH, and CH2COOH. Okay, this is what is known as itaconic acid. Another one, itaconic acid. Okay, which doesn't have any cis trans isomerism because it is these two groups are similar. CH2 here. Okay, so these are three products we got, and this can undergo a further reaction. Both of these can undergo further reaction. What do you know? You can guess. There are two COH in a very close proximity. It can undergo now dehydration, forming cyclic anhydride, isn't it? So minus H2O. So what do you get here? CHCO, double bond CO, and this becoming like this. That is a cyclic anhydride. What this called? Citraconic anhydride. And here also you get water is lost like this. The product now here is like this. CO, CH2, COO. This is called itaconic anhydride. So interesting series of reactions during pyrolysis. First it is losing water here, then losing carbon dioxide, and again losing water, dehydration. Right? So these are various reactions of citric acid. And finally, what are the uses of citric acid? See, citric acid has another important property that it can form very soluble, stable complexes, just like EDTA. Soluble complexes with heavy metal ions. Okay, so it is one important application is it is used in Benedict solution, Benedict reagent, you know that. Used to test aldehyde and reducing sugars. What is the reaction? If you add Benedict reagent and it gives you a reddish brown precipitate. What is Benedict reagent? It is a copper citrate complex, a blue solution. Okay, it's also used for easily testing urine sugar. So to copper sulfate, sodium citrate is added. So copper and citrate form complex, soluble complex. So that's an important application. Is used as a complexing agent used in Benedict solution. Another one is it is used as food preservative. Also, it is used as emulsifying agent. In medicines, citric acid is used, and it is used as flavoring agent, for giving lemon flavor. So, like that. Also, it is a mordant in dyeing and printing. it's used as a mordant in dyeing and printing. So these are various applications of citric acid. That's all for now. Thank you.